Hi everyone, welcome to goclasses. Is the audio video volume, is everything clear? Okay, good evening. So let's start now. What we are going to study in this lecture. So let's see. So in this lecture, we will study power of adjacency matrix. We know what is adjacency matrix. For any graph, we can represent using adjacency matrix. Also, we can represent using adjacency list. Okay. So in this lecture, we will see the properties of adjacency matrix. And when you do the power of adjacency matrix, means you have some adjacency matrix and you do the power of it. For example, m power 3, m power 4. Okay. So then what are the properties? What are the applications of power of adjacency matrix? This is the topic. This is the content for today. So first we will see the recap of what is walk, what is adjacency matrix. This recap we will see. Then we will see a very important result. And that is basically, it is a very important result, remember, about powers of adjacency matrix. And we will see the proof. Okay, next. Then we will see all applications of this result. So almost 7 or 8 applications we will see. So all the applications we will see, and then we will see questions, gate questions, variations. So these things we will see. So this is the content for this lecture. Now let me tell you something like, see, for a very long time, we have seen many concepts, many topics in the graph theory. Okay, all the topics, basically like independence number, like vertex cover number. So many concepts we have seen their proof. We have seen the analysis, the complete analysis of questions. Okay. And the relations between two concepts. Okay. So we have related the concepts. So a lot of things we have done in the graph theory, right? Okay. All the lectures of the graph theory, each and every lecture will improve your problem solving skills. Each and every lecture basically will improve your analytical skills. You can do the analysis. Okay. Because we have done the complete analysis of every question that we have seen, every gate question, every concept, every result, every theorem, every formula we have seen with proof, with complete analysis. So this is what we have done basically. Okay. Since we have started. Okay. From the first day when we started. Okay. After that, every lecture, every day, in every subject, we have improved basically our analytical skills, our problem solving skills. We have improved with every concept, with every lecture. Okay. And finally, let me tell you, this lecture that we will see today, this is the, I can say, father of analysis. Okay. This is going to be a pure analytical lecture. Let me tell you. So what you do, you take your copy pen, because in this lecture we will do complete analysis. We will do, as you can see, there are 7 or 8 applications we will see. For this, we will see one result, a simple result we will see. Then we will see the proof. If you skip the proof, that is fine. Okay. See, the result is very important. If you skip the proof, that is fine. But the applications that we will see, they depend on your problem solving skills. They depend on your analysis. Okay. So what you do, you take a copy pen and apply all the analysis that you have, basically you have improved your analytical skills. Those skills you apply today. This lecture is the father of all analysis. Okay. So basically after this lecture is over, then you can comment your review about this lecture, because in this lecture we will do a lot of analysis. Okay. This is a very interesting lecture. Let me tell you, this is not complicated. This is not hard. This is very beautiful lecture. Every application, you will see that every application is very beautiful. Okay. And you can easily find the proof of every application. Okay. So let's start now. Let's start. Okay. So let's start with the concept. Now, first, let's see the recap of adjacency matrix of a graph. Okay. Yes, we will see all the gate questions on this topic. All the gate 2022 question, 2021 question, all those we will see. So first, let's see the concept. What is the concept? Now, first we will see the recap of adjacency matrix of a graph. Any graph you can represent using adjacency matrix. Also, you can represent using adjacency list. Okay. So there are 2 standard representations of a graph. There are 2 very popular representations of any graph. One is adjacency matrix, another is adjacency list. So let's see what is this adjacency matrix representation of a graph. This is very simple. What you do. So for example, if you have a graph, let's assume you have an undirected graph. Let me, on one side, I am writing undirected graph. So let's assume you have undirected graph, and on another side, I will take one directed graph. So for example, let me assume that you have this undirected graph, that A, B, and C. This is your undirected graph, maybe D. Let's assume. So this is the undirected graph. Then what will be the adjacency matrix? In this situation, what is going to be the adjacency matrix? The adjacency matrix will be like this: A, B, C, D. What you do, basically, you put these vertices, all these vertices you put in one order. Okay, like you can fix any order. That is your choice. You can put them B, C, A, D. But whatever order you fix, that you should fix on the row and column. Okay. So basically, you should have the same order here and here. So for example, here you are putting ABCD, here also you put ABCD. Very simple. Now what you do? Now in this situation, the adjacency matrix you can easily create. You can see that A, B, these are adjacent. So you can say A, B are adjacent. Okay, so I can say that A, B are adjacent means there is edge between A, B. Okay, they are adjacent. There is edge between A, B. So you can just simply write that between A, B there is an edge. You can notice there is no self loop, right? Yes or no? You don't have any self loop. So because there is no self loop, so there is no edge between A, A. There is no edge, and between A, C there is edge, but there is no edge between A, D. So 0. Finally, you can see B is adjacent to A, and B is not adjacent to anyone else. C is adjacent to A. C is adjacent to A. C is not adjacent to anyone else. And then finally, you can notice D is not adjacent to anyone else. So this is the this is your graph. This is your adjacency matrix, correct? For this graph. So like this, you can create for the undirected graph. You can also notice that for the undirected graph, can you see this adjacency matrix? This is symmetric. Yes or no? For the undirected graph, because you have undirected graph, so this adjacency matrix, this is symmetric. Means if you notice, let's call it M. Let's call it M. Then you can easily see that M is equal to M transpose. Okay, M will be equal to this matrix is equal to M transpose. You can easily see. Now let's see for directed graph. Let me take one directed graph that like this type of directed graph. Let me take. Let me okay. So you can take this directed graph. You can take. Then finally your adjacency matrix will be what? The similar idea you will apply. Again, you can put the vertices in some order, in some fixed order. You can put them, and then what you can do? Then you can notice that from A to B there is edge. So from A to B there is edge. There is no edge. From A to C there is edge. So I can say from A to C there is edge. So like this, from A to D there is no edge. Okay. Similarly, there is no edge from B to anywhere. There is no edge from C to anywhere. There is no edge from D to anywhere. So this is your. And can you notice that for a directed graph, this may not be symmetric. This is not symmetric, right? Yes or no? For the directed graph, because this is a directed graph, from A you can go to B, but from B you cannot go to A. Okay, so there is edge from A to B, but there is no edge from B to A. So you can easily see that this is not a symmetric matrix. Okay, so this is how you can create the this is your concept of adjacency matrix. So adjacency matrix simply means that if you have edge from A to B, if you have edge from A to B, then you put this A, B entry, you put 1. If there is no edge from A to B, A to D, if there is no edge, then what you do? From A to D, you put this 0 entry. So this is a simple concept of adjacency matrix that we already know. Like for example, you can see here, this is your graph. This is undirected graph. Now for this graph, you can easily create the adjacency matrix, and the adjacency matrix is like this. You can put the vertices like this, A, B, C, D, A, B, C, D. So you can put the vertices in fixed order. In this order, you are putting in this order A, B, C, D. So here also in the column also, you put in the same order A, B, C, D. Okay. So basically this ordering of vertices you follow now. So you can easily see that this is the adjacency matrix for this graph. There is no edge between A, D. There is no edge here, A, D. So you can see this is 0 here. There is edge between A, C. So you can see there is 1 here. There is no edge. There is no self loop. Because there is no self loop, so there is 0. Because there is no self loop between B, B, so there is 0. So this is how you can create adjacency matrix. Similarly, you can create adjacency matrix for a directed graph. If you have a directed graph like this, then for this directed graph, the adjacency matrix will be this. Okay. For this directed graph, this is going to be the adjacency matrix. You can again see that these are the vertices A, B, C, D, A, B, C, D. These are the vertices. Now you can easily see that from A to B, there is edge. Okay. From B to C, there is edge. From C to D, there is edge. And from D to A, there is edge. Okay. So this is your adjacency matrix. You can easily see this is your adjacency matrix for this directed graph. Okay. Is this clear? Tell me. Is this clear to everyone? For this directed graph, this is the adjacency matrix. So this is the concept of adjacency matrix of a graph that we already know. And this is very simple concept. You can take this as a homework. You can see that for this graph, this will be the adjacency matrix. And the vertex ordering is basically V1, V2, V3, V4, V5, V6. Okay. The same ordering you follow here, V1, V2, V3, V4, V5, V6. Okay. So you can easily see for this undirected graph, this is an undirected graph. And for this, the adjacency matrix will be this. You can easily check. Similarly, for this directed graph, this will be the adjacency matrix. You can check. You can see that from V1, there is only one outgoing edge. From V1, there is only from V1 to V2. You can notice. So from V1, there is only one outgoing edge. So that is the reason from V1, there is only V1 to V2, there is one. All the remaining entries are zero. You can easily see. Okay. So this is the concept of adjacency matrix. Now we are done. Now for undirected graph, these are the properties. Let's see some properties. If the graph is undirected, then what will happen? Tell me. If the graph is undirected, then what will happen? Then the adjacency matrix will be symmetric. Means it will be same as its transpose. It will be symmetric. The second, you can notice that if you don't have any loops in the graph, if you don't have any self loops in the graph, then you can easily see if you don't have self loops, if you don't have these self loops, then the main diagonal entries will be zeros. Okay. All the main diagonal entries will be zeros if you don't have self loops. Similarly, of course, if I give you adjacency matrix, then you can create a graph. Okay. So graph can be reconstructed from the adjacency matrix. So these are some points. These are some properties. Now let's move on to the next concept. The next concept is walk in a graph. This is the next concept. What is walk in a graph? That we have already seen. I told you walk basically means that vertex and edges can repeat. Yes or no? Correct. Like if I give you a graph, for example, let me assume that you have this graph A, B, C, D. Okay. So maybe you have this graph. Now in this graph, you can notice there are in a walk. What are the walks? In a walk, vertices and edges can repeat. Okay. So vertices and edges, those can repeat. Now, Mavit is asking very nice doubt. Multiple edges are not allowed. See, basically everything that we study in this lecture, okay, for all the graph, we will assume that we don't have multiple edges. Okay. So Mavit, everything that we study in this lecture, everything, okay, we will assume that there are no multiple edges between two vertices. Okay. Basically. So, okay. Remember, note that, in all graphs that we consider, in all graphs that we consider, whatever graph we consider, okay, there are no multi-edges. There are no multi-edges. Multi-edges means there are no multi-edges. Multi-edges means, so if you have directed graph, this is not allowed. Like if you have a directed graph, then you cannot have this. If you have directed graph, then let's assume A, B, then you cannot have this. Okay. So these are the multi-edges. Okay. So this type of edges are called multi-edges. This type of edges are called multi-edges. Remember, for a directed graph, this is not multi-edges. For a directed graph, this is allowed. Please understand that for a directed graph, this is fine. Like for example, there is one edge from A to B. There is one edge from B to A. These are fine. These are not multi-edges. Okay. These are different edges. These are fine. These are different edges. These are different. These are different edges, but these are same edges. So basically multi-edges means same edges. Okay. So you cannot have same edges. So remember, these are different. These are allowed. Like these are, I can say these are allowed. Okay, so these are allowed and these are not allowed. Okay, these are allowed. And so these type of multi edges are not allowed. Like same edges are not allowed. For example, in undirected graph, if you have undirected graph, then this is not allowed. Like you have A, B, and this type of situation is not allowed. Okay, so this type of things are not allowed. So I hope this point is clear, that all the graphs that we consider, there are no multi edges. We don't have any multi edges. Multi edges means same edges. We don't have any multi edges. Everything else we will consider. We will consider directed graph. We will consider undirected graph. We will consider self loop also. Everything else we will consider, but multi edges we don't allow. Okay, all the graphs that we will consider, there are no multi edges. Now let's move on. Now let's see the concept of a graph, walk in a graph. What is this concept? Walk in a graph. So I told you that in a walk, repetition of vertices and edges is allowed. Yes or no? A walk may repeat both vertices and edges. So walk is very simple. The simple concept, like you are walking in a park, correct? Tell me, when you are walking in a park, then can you repeat the same track or same point? When you are walking in a park, then can you repeat this track? Yes, you can repeat. So very simple. Walk simply means that you can repeat. Okay, you can repeat edges, you can repeat vertices. So for example, you can easily see that this is a walk. I can say from A you can go to B, from B you can go to A. So this is a walk of, I can say, two length walk. Two length walk, because length of walk means number of edges. So how many edges are there? So there are two edges. So that is the reason this is a two length walk. So for example, you can have, this is one length walk. This is one length walk. For example, A to B, you can go to C, then you can go to D. This is a three length walk. This is a three length walk. For example, you can go to A to B, then you can go to C, then you can go to B, then you can go to D, then you can go to C. This is also a walk. Okay. This is also a walk. You can easily see that this is a five length. This is a five length walk. So the concept of walk is very simple, that basically it is just a sequence of vertices and edges. Okay, it is just a sequence of vertices and edges such that they are adjacent to each other. For example, you can go from A to B, then you can go from B to C, then you can go from C to D. This is a walk. Similarly, you can go from A to B, you can go to C, then you can go to B, then you can go to D, then you can go to C. This is also a walk. Okay, basically walk is everything. Like whatever you do, that is a walk. Okay, as long as you are consecutive, you are walking consecutively. Okay, so walk basically means a sequence of vertices comma edges, a sequence of vertices comma edges such that they are adjacent. Like for example, this B comma C, they must be adjacent. For example, this edge and this edge, they must be adjacent. Okay, so like this is the concept of walk. Very simple concept. So the concept is very simple. Like this is just a list of vertices and edges such that you can notice they are basically adjacent. The length of walk, what is that? That is the number of edges in the walk. How many edges are there in the walk? Okay, that is the length of the walk. This is the definition. You can notice in a walk, vertices and edges can repeat. So let me ask you some simple questions. Like consider this question. Let's see. Consider this simple question. You consider, find the number of walks. How many walks are there of length 3 from vertex A to vertex A in the following undirected graph? I am giving you one undirected graph, A, B, C. How many walks are there of length 3? Can you tell me? How many walks of length 3 from A to A? From A, you have to go to A and you must visit 3 edges. You must have 3 edges. So tell me, how many walks are there? How many number of walks? How many walks of length 3? How many walks of length 3? Length 3 from vertex A to vertex A in the following undirected graph. So you can walk of length A from A to A, length 3. So how many? The answer is very simple. The answer is 0. Okay, so the answer is basically 0. There is no, so the answer is 0. So from A to A, the walk of length 3, this will be 0. right? Yes or no? So zero walks, I can say zero number of walks. So okay, that is zero. I can say number of walks, number of this type of walks is equal to zero. Okay, is this clear? Because you can easily see that from A, if you want, basically you want three edges, right? Yes or no? You want three edges. So what you can do, you can go to B. So you can do this. You can go to B, then you can come back to A. Now what? Now what? Now what? Now what? Now you can go to C, but now you, so at least four edges you need. Are you getting my point? Either four edges or two edges. Okay, yes or no? Is this clear? So either four edges or two edges. For example, you can have two edges. So two edge walk, two length walk you have. This is two length walk, or you can have, four length walk. So two length walk, four length walk, but number of walks of length three, that is zero. Okay, is this clear? Length three walks. I am asking length three walks, that is zero. Now let's see the next question. Let me ask you the next question, and that is, uh, let me ask. So how many walks of length two? How many walks of length two from A to A? So what is that? From A to A, how many walks of length two? So that is, there are two. Yes or no? Either you can put B here or you can put C here. So there are two walks. So the answer is going to be two. Is this clear? Very simple. Now let's see the next concept. Next question. Tell me the answer now. Now tell me the answer. For this question, what will be the answer? So how many walk of length three? How many walks of length three? I am asking how many walks of length three, means from A you want to go to A, something like this, from A to A. So what is the answer? So the answer will be, so what you can do, either you can go from A to B. Okay, either you can go from A to B, then you can go to C, then you can go to A, or you can go from A to C, then you can go to B, then you can go to A. So the answer will be 2. Is this clear? So answer will be 2. Is this clear? So let me know. So you can see from A you want to go to A. These are the things you have to fill. These are the things that you have to fill. So the answer will be 2. So there are two walks. From A to A, there are two walks. Okay. So either you can go like this, either you can go, or you can go like this, you can go. So there are two walks from A to A. So very simple. Now let's see another question. For example, A, B, C, and now this. Now tell me the answer. How many walks of length 3? How many walks of length 3 now? From A to A. I'm asking from A to A, how many lengths of 3? How many walks of length 3? So now what you can do, now you can go from A to A, then you can go from A to A. Okay, so this is one walk. Yes or no? Now you can go, now you can do this. This is one walk of length 3. Or what you can do, okay, or what you can do, you can go to B. From A, you can go to A, then you see from A, you can go to A, then you can go to B, then you can come to A. Are you getting my point? Okay, very simple. So basically now you can use this loop. This loop you can use, or what you can do, the same thing you can do, but what you can do, like, for example, you can go to B, then you can come back to A, then you can come back here. Okay, so either you can do like this, or you can do the same thing with C. You can do the same thing with C. You can do like this, or you can do the like this. For example, this is also you can do, or you can do this walk, or you can do this walk. Okay, so basically there will be total how many? Total there will be 7. Yes or no? Total there will be how many? So, or you can do this, from A you can go to B to C to A, or you can go from A to C to B to A. So tell me how many walks are there? You can do this, or you can do this. Is there any other? Is there any other? Tell me. Like, can you create something else? Is there any other possibility? Can you create something else? Can we create something else? No. Okay, so only these are the things that we can create. So the number of walks will be 7. Please tell me, is this clear? So number of walks is going to be 7 of length 3 from A to A. From A to A, there are 7 walks of length 3. Is this clear? Let me know. So very simple. Are you understanding the concept of walk? The concept of walk, did you understand? Please tell me. A simple question, let me ask you again. Like you have this graph, A, B, C. Okay, how many walks of length 2? From A to A. Number of walks of length 2 from A to A. What that will be? From A to A, how many walks of length 2? I'm asking number of walks of length 2. So either you can do this, either you can do this one, or what you can do, you can go to B, then you can come back to A, or you can go to C, you can come back to A. So there are 3, correct? There will be 3 walks. So the answer will be 3. Okay. The same thing we can ask for, like from A to C, how many walks of length 2? From A to C. Tell me the same question I can ask you, but I can ask you for A to C. Now what? From A to C. Then what you can do? Length 2 you want, remember. You want length 2. So something like this you want. So what you can do? Either you can just put A. This is the only thing you can do, right? This is the only thing you can do. So the answer will be 1. Okay. Length, oh, sorry. Or you can do this. Okay, sorry. You can also do this. So there will be 2. Okay, either you can do AAC or you can do so AAC. Basically, it is like this. Okay, this is the template. The template is this. Now either you can put A here or you can put B here. Okay, in this you can either put A or you can put B. So the answer will be 2. This is the template. Okay, so let's move on now. So I hope you understood the concept of walk. This is very important. This is going to be very important. Okay, so this concept of walk, finding the number of walks, is that clear? Let me know. Is that clear to everyone? So what is the number of walks? So this is going to be very important thing, number of walks. So very easy concept. Now let's move on. Before we move on, you tell me a simple thing. A simple thing I want to ask. It is an interesting analysis actually. It is a very interesting analysis that, let me give you this graph, A, B, C, D. Okay, in this graph, what is the number of vertices? What is the number of vertices? That is basically 4, right? Okay. Now, in this graph, I am asking a simple question that, first of all, before I ask you this question, if you have n vertices, then what is the, I can say, let's assume you have n vertices. You have n vertices undirected graph. You have n vertices undirected or directed, basically any graph. Okay, see n vertices graph. First of all, whenever I write graph, it automatically means that I am considering directed comma undirected, both of them. Okay, this is something I want to tell you, that in this lecture we will consider, whenever I write a graph, okay, then we will consider that it can be directed or undirected. Is this clear? Basically, in this lecture, okay, graph means what? This graph, it automatically means what? Graph means directed or undirected. Is this clear? The graph means directed or undirected graph. Okay, so this is something important, because in most of the time you can notice in the graph theory we consider undirected graph, right? Yes or no? In the graph theory, most of the time we only study undirected graph. But in this lecture, okay, whenever I say graph, whenever I say graph, it automatically means either it is directed or it is undirected graph. So if I want to say directed, then I will mention directed. If I want to say undirected, then I will mention undirected. Basically, in this lecture, I will mention everything. No assumptions. Is this clear? In this lecture, don't make any assumptions. I will mention everything. If I want to speak about directed graph, I will mention it. If I want to speak about undirected graph, I will mention it. So in this lecture, graph means, and also in this lecture, no multi-edges. Okay, no multi-edges. Self loops is fine. In this lecture, we consider self loops. Okay, we will consider self loop, but we will never consider multi-edges. Okay, let's move on. So a simple question I want to ask: if you have an n vertices graph, okay, then what is the maximum length what is the maximum basically length what is the maximum distance between two vertices? Tell me, what is the maximum distance between two vertices? If connected. If it is connected, then what is the maximum distance? If it is connected. Okay. So whether it is directed or whether it is undirected, then if you have basically, if you have connected or weakly connected, I can say, if it is connected or when connected means in case of undirected, okay, if connected undirected, if connected undirected, or weakly connected directed. Okay, so this is what I'm saying. I'm saying that basically what is the maximum distance. Okay, what to do? Let's just consider undirected graph. Okay, let me consider only undirected graph. So tell me, for undirected graph, what is the maximum between two vertices if it is connected? What is the maximum distance? The maximum distance that you can have, is basically n minus 1. Okay, this is the maximum distance you can have between two vertices if it is connected. Okay, correct. So very simple. Now the next question I want to ask, this is your number of vertices, that is 4. Now in this graph, you can see that if I want to check whether it is connected or not, then what I will check, tell me, like what I will check if I want to check it is connected or not. You have undirected graph. Let me ask you a simple question. Let's assume you have undirected graph. You have this undirected graph. Okay, and I want to check if it is connected or not, to check if it is connected or not, okay. So what I can do, this is something I can do. What I can do basically to check if it is connected or not, this is something I can do. Between every two vertices, between every pair of vertices, what I can do, between every pair of vertices, I can find walk. Yes or no? Find some walk. Correct. Find some walk. I'm discussing undirected graph. So what you can do, you can basically, for undirected graph, if you want to check whether it is connected or not, then what you can do, between every two vertices, you can find some walk. Now, this walk, tell me, in the worst case, what is the length of walk I will search for? Find walk from length 1 to, tell me, okay, from length 1 to, in worst case, I will search for n minus 1. Yes or no? In worst case, I will go, in worst case, I will search, I will try to find some walk from length 1 to length n minus 1. This is the worst. Like, there is no need to find the walk of length n. Yes or no? Correct? Yes or no? Agree? There is no need to find walk of length n. So very simple that this is something you will do, that between any two vertices, whatever two vertices you will do, you will try to find, okay, basically to check if it is connected or not. Between every two vertices, you try to find some walk from length 1 to n minus 1. There is no need to find walk of length n. So definitely I can say there is clearly no need, okay, to find walks of length greater than equal to n. So very simple. So you can say, save some time, and this is the maximum you need to do. Now, another question I want to ask, like in this graph, you can see that there is a walk from A to D. That is like, if I only find walk of length 3, can I say graph is connected? If I only find walk of length 3, can I say graph is connected? If we find walk of length 3, if we find walks of length 3, walks of length 3 between every two vertices. Can I say graph is connected? Can I say graph is connected or not? If we find walks of length 3, I am saying walks of length 3, not like length of 1 or 2. I ignore length of 1 or 2. I only find walks of length 3 between every two vertices. Okay, then can we say connected or not? Then can we determine connectedness or not? Can we determine connectedness? Connectedness in a graph? In a undirected graph? Tell me. Can we determine? Can we determine connectedness in a undirected graph? Tell me a simple question. Can I determine that? By only finding walks of length 3. By only finding walks of length n minus 1. I don't find walks of length 1 or 2. I am only finding walks of length 3. Like between every two vertices, I just find walks of length 3. Then can we determine connectedness in undirected graph? The answer will be no. Yes or no? The answer is going to be no, because you can easily see that between a comma d there is a 3-length path, 3-length walk. But you can notice, like for example, between a comma b there is no I can say 1 2. Okay, so 1 2. Between a comma c there is no walk of length 3. Yes or no? Between a comma c you can see there is no walk of length 3. Are you getting my point? Like in this question, you can easily see that between a comma c there is no walk of length 3. Tell me, did you get it? What I'm saying? So you can easily see between a comma c no walk of length 3. No walk of length 3. So can I say that if you only check walk of length n minus 1, that will not work? Can I say if you only check walk of length n minus 1, that will not work? Agree? Is this clear to everyone? If you only check walks of length n minus 1, that will not work. So only checking, remember, only checking walks of length n minus 1 between every pair of vertices may not work, or I can say will not work. Correct? Okay. So if you only check these, if you only check walks of length n minus 1 between every pair of vertices, that will not work. That will definitely not work. Okay. Because you can easily see here in this example, between a comma c, there is no walk of length 3. Between a comma c, we have no walk of length 3. So this is not going to work. So what will work? So this will work. Remember what will work? From length 1 to length n minus 1. This is what we have to do. Yes or no? So what we have to do? So we have to remember, if you I can say, so we have to find. So basically this is, I can say, connectedness. If you want to check connectedness of undirected graph, if you want to check this, if you want to find out this connectedness of undirected graph, then what you have to do? You have to find walks. This is what you have to find. You have to find walks of length 1 to n minus 1. Okay, is this clear? Basically find walks of length 1 to n minus 1. These walks between every pair of vertices. Between every pair of vertices. Now something interesting I'm going to do. Something interesting. Something very interesting. Like let's assume there is someone, and there is someone who knows how to find n minus 1 walk. See, are you getting my point? Let's assume there is someone who knows how to find walks of length n minus 1. He does not know how to find walks of length n minus 2. walks of length 1, walks of length 2. There is some algorithm, there is some way you can get walks of length n minus 1. Okay, are you getting my point? What I'm saying? Are you getting? I am saying that there is someone, let's assume Mavith. So Mavith knows that how to find out walks of length n minus 1. You have a graph, n vertices are there, undirected graph you have. Okay, in that you have n vertices, undirected graph with n vertices, and let's assume Mavith knows that how to find out walks of length n minus 1. He can tell you, is there walk of length n minus 1 or not? Now, what something smart, like some smart approach, what you can do such that you can solve your problem of connectedness. Like, are you getting my point? Is this clear? So there is some algorithm, there is some way I can find walks of length n minus 1 or not. Okay, some algorithm will tell me there is walk of length n minus 1 or not. But I want all the walks from length 1 to length n minus 1. All the walks I want, correct? I want all the walks. I want from 1 to n minus 1. I want all the walks. There must be at least one walk from length 1 to n minus 1. There must be some walk. Okay, I want all of them. Then something smart that I can do. Let's see. That's something smart. Let's see. That something smart is this. What I can do? See this smart way. Just put self loop. Just put self loop. Okay, now something smart will happen. Now you can easily see, once I put the self loop, then something interesting will happen. What is that? This will happen that now automatically you will have walk of length 3. If you have previously, if you like in this graph, see, in this graph, if you have walk of length 2, then in this graph you will have walk of length 3. New graph you create, just create this new graph. And what I'm saying that this is your G and this is your G dash. Now I'm saying that in this, if you have any walk, if you have any walk from length 1 to 3, like for example, there is a walk between A comma C length 2. Now that will now automatically you will get walk of length 3 here between A comma C. What? Okay, just wait one cycle. This cycle you can waste, correct or not? Yes or no? This cycle this loop you can waste. This loop you can waste. Is this clear what I'm saying? So if there is a walk here from length 1 to n minus 1, then there will be walk here of length exactly n minus 1. Is this point clear? Like for example, another example, let's see. So you can see this. Another example, you can see there is a walk. Okay, automatically this walk you can just waste some cycles. Waste some cycles. Tell me, is this method? Did you understand this method? What I'm saying? Okay, so this is something I want to tell you, that let's assume you have an undirected. Let's assume you have an undirected graph G. This is the undirected graph G you have. Okay, undirected graph G that you have. Now I am saying that if and this undirected graph G you have, and from this I am creating a new graph. I am creating a new graph. Okay, by putting self loops on all vertices. By putting self loops on all vertices, I am creating a new graph. Let's say that is G dash. Okay, a new graph I am creating by putting self loops on all vertices. Now, what is this property? What this G dash will have the property? So this G dash will have the property that if there is a walk, of length 1 to n minus 1 in G between A comma B, then there is a walk of length n minus 1, exactly n minus 1. Okay, then there is a walk of length exactly n minus 1 in G dash. Tell me, is this clear or not? This is something interesting. This point is interesting, and this will be useful in the future. This point will be useful. So tell me, did you understand this or not? Is this point, did you understand this point? A simple point I am saying that you have a graph. Let me take another example. Consider any graph you can consider. For example, A, B, C, D, E, F. Consider this graph. Now in this graph, you can easily see, let's call this graph G. Let's call this graph G. Now, what you do in this graph G, you can see that there is a walk of length 1 between A comma B. There is no walk of length 2. Correct or not? Between or I can say between let's see two vertices. For example, between A comma B, do we have 1, 2, 3, 4, 5? Do we have, so how many vertices? You can see their n value, the number of vertices is 6. So is there any walk of length 5 between A comma B? Is there any walk of length 5? Is there any walk of length 5 between A comma B? So you can go from A to B. Yes, the walk of length 5 is there. Okay, between A comma C, do we have walk of length 5? You can do this, then you can one, 2, 3, 4. Okay, so between A comma C, there is no walk of length 5. Yes or no? Between A comma C, so you can easily see between A comma C, no walk of length 5. Correct? No walk of length n minus 1, which is 5. No walk of length n minus 1. Correct? Is this clear to everyone? But there is a walk. But there is a walk of length how much? But there is a walk of length 2. Walk of length 2. There is no walk of length 5, but there is a walk of length 2. Now what you can do, you can simply say that this G you can transform into G dash, and what you do, just make self loops. Now just make self loops on every vertex. Now something interesting will happen, and what is that? Something interesting will happen. What is that? That now you can notice that because there is a walk of length 2, because there is a walk of length 2, you can see there is a walk of length 2, like this is the walk of length 2. Now this walk, you can just waste some cycle on A. Correct or not? Are yes or no? Some cycles on A you can waste. You can waste some cycles on A. That's it. Now you got a walk of length how much? 5. Can you see? Walk of length 5. Is this clear to everyone? Let me know. Is this point clear to everyone? See, simple point I am saying that if you have self loop, then just waste some loops, just waste some cycles, some self loops you can waste. If there is a walk of length L between two vertices in G, then by putting all self loop, then we will get a walk in G. Okay, no, Himanshu, my target is that this n minus 1 is my target. My target is this. Okay, so a simple, this is a simple point. Again, I will revisit this point. Okay, just wait. This point I will again revisit. Okay, this is the point. You can see you have undirected graph G. In this undirected graph, if you put all the self loops, then what will happen? If there is any walk from A to B, if there is any walk at all, okay, if there is any walk at all, I can say if there is any walk at all between A comma B, if there is any walk, if there is any walk at all, if there is any walk at all in G between A comma B, then there is a walk of length exactly n minus 1 in G dash. This is something I want to tell. Is this clear? Like in G, if there is some walk between A comma B, like now that walk can have length 1, 2, 3, 4, n minus 1. That walk can be of any length, yes or no? But if I put all the self loops, then I can say that I only have to check exactly n minus 1 length. Okay, this point I will revisit. What I will do, this point that we have seen, this I will revisit again. In future, I will again tell you this point. So just don't worry. If you understood, very good. If you did not understand, for now, forget about it. In this lecture, as in future, you will understand this. Okay, so let's move on now. Now let's see very important result. That is powers of adjacency matrix. This is very important result. As you can see, very important. Okay, let's see what is power of adjacency matrix. So we will see this for both of them, like directed graph or undirected graph. Whatever graph you take, whether you take directed or undirected graph. Okay, for directed or undirected graph, whether you take directed or undirected graph. What can we say when you do the power of adjacency matrix? So let's see this one. So first of all, you tell me, for any graph, directed or undirected, the graph can be directed or the graph can be undirected. If I do power 1, then what I will get? If I do power 1, what I will get? If I do power 1 of adjacency matrix, then I will get adjacency matrix itself. Yes or no? So let's assume there is an adjacency matrix M. Now, if I do power 1, then that will be same as M. Can I say that if you do power 1, you are getting walks of length 1 between any two vertices? Can I say? Like, are you getting my point? Basically, this adjacency matrix is giving you walks of length 1. This is giving you walks of length 1 between every pair of vertices. Correct or not? Between every pair of vertices. Yes or no? Okay, if you do power 1, basically that is same as your adjacency matrix. So that is giving you walks of length 1. That is giving you walks of length 1 between every pair of vertices. For example, let's take this graph A, B, C, D, self loop. So let's see this graph. Now in this graph, you can easily see your adjacency matrix. What that will give you? Your adjacency matrix, power 1. This is your adjacency matrix M. What it will give you? It will give you walks of length 1. Like how many walks of length 1 from A to A? From A to A, how many walks of length 1? Tell me. How many walks of length 1 from A to A? So yeah, you can take disconnected also, no problem. You can take E. Let's take E also. Simple question I'm asking, how many walks of length 1 from A to A in this graph? Like this is your graph A, B, C, D. Okay, C has, let's assume this C has self loop, and this is E. So this is simple question that what is the number of walks from A to A of length 1? How many number of walks from A to A of length 1? The answer is only 1. Okay, that is because you can go from 1 to 1. There is a self loop. There is a self loop, so you can go from 1 to 1. The same question, can I ask you the same question? How many walks from A to E? From A to E, how many walks of length 1? From A to E, how many walks of length 1? The answer is 0. The answer is 0. Okay, how many walks of length 1 from A to D? From A to D, how many walks of length 1 from A to D? From A to D, that is also 0. Okay, so what I'm saying that basically, let me make a table. Let me make a table. What I will create. So here I'm writing number of walks of length 1. Okay, and here I'm writing between what? From where to where? From 2. Okay, so you tell me, like for example, from A to A, you can easily see from A to A, there is only 1 walk. Okay, from A to B, how many? From A to B. From A to B, how many? From A to B, there is 1. Okay, from B to B, how many? From B to B, how many? From B to B, there is 0. Okay, from C to C, how many? From C to C, there is 1. From E to E, how many? There is 0. Okay, so is this clear? Like the adjacency matrix is telling you how many walks you have of length 1. Can I say? Is this clear to everyone? Please tell me. Adjacency matrix, basically this adjacency matrix tells you how many walks of length 1 you have between every two vertices. Okay, between every two vertices, how many walks of length 1 you have. For example, here, this adjacency matrix will give you like how many walks of length 1 from A to A, that is 1. You can notice this adjacency matrix will give you, this adjacency matrix is already giving you number of walks from A to anywhere. Okay, from A to anywhere, like from A to E 0, from A to D 1, from A to C 0, from A to B 1, from A to A 1, from B to B 0, from B to A 1, from B to C 1, from B to D 0, from B to E 0, from C to C 1, from C to B 1. Okay, then 0, 0, 0. Next, you can notice from D to A, that is 1, from D to A 1. Then everything else is 0, 0, 0. From E, everything is 0, 0, 0, 0. So is this clear? Can I say that power 1 if you do, basically your adjacency matrix, your adjacency matrix gives you walks of length 1. Walks of length 1 between every two vertices. Okay, let's move on now. The next concept, next question. If you do power 2, then what will happen? If you do power 2, means m power 2. If you do this m power 2, then what will happen? M power 2 means matrix multiplication, right? Yes or no? Matrix multiplied by matrix. This is your matrix multiplication. This is your matrix multiplication. So tell me, if you do this, now see, okay, just take your copy pen if you want, or you can just understand like this. See this, if you have an adjacency matrix, this is your adjacency matrix. Let's assume like, for example, ABC or ABCD. And here you have adjacency matrix like ABCD. This you multiply with another adjacency matrix, which is ABCD. And here you have ABCD. Okay, now you tell me a simple question I am asking. Focus on this entry. Which entry? Focus on this entry. Basically, the multiplication will give you some matrix. The multiplication will give you another matrix, ABCD, ABCD. Okay, just focus on this entry. What I'm saying, just focus on this entry. On this entry, you focus. Okay, now you tell me, for this entry, what will happen? What will be calculated for this entry? For this entry, what will be calculated? If you focus on this entry, for this entry, you can notice this row will be multiplied with this row, correct? Can you notice this row will be multiplied with which row? This row will be multiplied with this row. This row will be multiplied by this column. Yes or no? This is what happens in the matrix multiplication. Do you remember the matrix multiplication? Like if you do the matrix multiplication, you have some matrix A you have multiplied by some matrix B. This is some matrix B you have. Okay, so there are two matrices. One matrix is A, another matrix is B. Then the resultant will be C, the matrix C, the matrix will be C. Now in this matrix, what will be Cij entry? This is Cij. This Cij entry will be ith row of A, okay, this ith row and this jth column. This jth column of B. Yes or no? Is this clear to everyone? Please tell me. This is what happens in a matrix multiplication, right? Okay, the ith row of A will multiply with jth row of jth column of B. Then you will get this. Okay, I can say ith row of A multiplied with jth column of B. This is what happens. Now the same thing you do here. So you can easily see that. Now what value you will get here? See, if there is 0 here, you tell me, if there is 0 here, then it does not matter what you have here. Yes or no? It does not matter what you have here. Can I say that if you have 0 here, in this, if this value is 0, then it does not matter what value you have here. It does not matter that value. Okay. So if this value is 0, then definitely there is no contribution here. Because of this value, there is no contribution here. So just focus on the contribution. When the contribution will happen? Just focus on the contribution. When the contribution will happen? The contribution will happen when you have this value 1 here and this value is also 1 here. Then the contribution will happen, correct? Do you agree? These two will give you the contribution. Okay, please understand very simple thing. These two will give you the contribution. Or this is 1, this is 1. Then also the contribution will happen. Then also contribution will happen. In this situation, the contribution will not happen. For example, if this is 1, this is 0, then the contribution will not happen. Okay, in these situations, the contribution will not happen. These are the, okay, so finally I can say that this value will come as 2. This value is coming to why? What is the reason? Because this value is coming to, because this is telling you what? Look at this. Because there is from C to C, there is one edge. From C to C, there is one edge. And from C to D, there is one edge. Okay. Similarly, from C to D, there is one edge. From C to D, there is one edge. And from D to D, there is one edge. So that is the reason. That is the reason this value 2 is coming. So this value 2 is telling you, this value 2 is telling you number of walks from C to D of length 2. Number of walks of length 2. Number of walks length 2 from C to D. Yes or no? This value 2 is telling you number of walks of length 2 from C to D. Please tell me, is this clear? A very simple point. Okay, this is a simple point that you can generalize this also. If you want, you can generalize also. For example, if you have, like, let's assume this is 1 here, and let's assume this is 1 here, this is 0 here, this is 1 here. Okay, and let me assume that you have 0 here, 1 here, 1 here, 0 here. Let me assume you have this situation. Then what will be this value? Then what will be this value? Tell me what this value will be. This value will be equal to, you can easily see that. Okay, because of this, there is no entry. Because of this, there will be one value. So the answer will be 1 only. Here you will get only 1 because there is only one walk. Actually, there is only one walk. Look at this and look at this. Okay, if you look at this, from C to B, from C to B, from C to B, and from B to D, from B to D. So there is one walk. Only one walk of length 2. Okay, is this clear? Same thing you can basically, you can continue. The same thing you can continue. So finally, what I'm saying that whatever graph you have, this is the final conclusion. This is important, that you have a graph. This graph G can be directed or undirected. This graph can be directed or undirected, does not matter. Simple or loops, does not matter. So you have a graph G. In this graph G, for this graph G, let's assume you have adjacency matrix. This adjacency matrix is M. Okay, for this graph G, that adjacency matrix is M. Okay, now what we are saying that this M power 2, if you do, what this M power 2 will tell you? This M power 2 gives, okay, what it gives? It gives a number of walks of length 2, between every pair of vertices. Every pair of vertices. Is this clear? Please tell me. Let me know. Is this clear to everyone? So you can notice the M square, the M power 2. It will give you number of walks of length exactly 2. Number of walks of length exactly 2 between every pair of vertices. This is what this M square will give you. Okay. So now this will give you number of walks. This will give you number of walks. Mavit, this will exactly tell you how many walks are there of length 2. Okay, let's take example. With example, you will understand. See, consider this example. Let me take one example of directed graph. This directed graph you take. Let's assume that you have this directed graph. Let me also take self loop. You can take self loop. Okay, so consider this directed graph, and you can take this. So let's assume this type of graph you have, and let's assume self loop. Now tell me what is M? For this graph, what will be M? The M will be what? The M will be ABC, ABC. So something like that, ABC, ABC. The M will be what? M will be 1, then 1, and then 0. Okay, from B, you can notice that from B to C there is, and then from C to C there is 1, and from C to A there is 1, and there is 0. Now you do M square. So tell me what will be M square? What is going to be M square? Can you tell me? Can you tell me what will be M square? Let's see M square. 101, you multiply this with M. So what that will be? That will give you what? So you can notice this row will multiply with this column. This first row will multiply with this first column. So what you will get? Because of this, you will get 1, right? You will get 1. Why you are getting 1? Can you tell me why you are getting 1? Because there is only one walk from A to A of length 2. See, from A to A of length 2, only one walk is there of length 2. This is the only walk that you have. Isn't it? Isn't it? Tell me. Are you getting my point? So you can easily see how many walks. Okay, so basically just find it out. You can easily see what is the number of walks. I'm asking you back to back. You just tell me what is the number of walks of length 2. Okay, what is the number of walks of length 2 from A to A? Tell me, from A to A, how many? How many walks of length 2? You want length 2. There is only one, and that is like from A to A, then A to A. There is only one of length 2. Okay, now tell me, from A to B, how many? From A to B, how many you have? How many you have from A to B? So what you can do, you can go from A to A, then you can go to B. So again, there is one. Next, from A to C, how many you have? From A to C. From A to C, again, there is only one. You can go from A to B, then you can go to C. Okay. From B to B, how many? From B to B, tell me. From B to B, how many you have? Of length 2. You want length 2, that is 0. There is no walk of length 2. From B to A, how many? From B to A of length 2, there is 1. Okay, there is one, that is B to C, and then C to A. Next, from B to C, how many? From B to C, you can go from B to C, and then you, okay, so there will be 1. Yes or no? And are you getting my point? C, from C to C, how many? From C to C, there will be 1. You can go from C to C, then you can go to C. So there will be 1. Okay, so like this. Now you can easily see this will be same as this M square. You find this M square, that will be same as this data. M square will be same as this data. Okay, so you can just simply find the M square, and this you can easily see this will multiply with this. So then what you will get? 110. So that again will 1, and then you can multiply this with this, so 1. You can easily see that this is the same data you are getting here, 111. The same data that you are getting here. Next, similarly, what about this one? So this you can multiply with 101, then you will get 1. 001, here you will get 0, and 001 you multiply with this, that will be 1. And this is the same data you are getting, like from B to ABC. From B to ABC, this is the same data, 101. The same data you are getting, 101. And similarly, from this you can notice 101. So this will give you 2. This will give you 2, means from C to A, how many? And you can check it out. You can check it out from C to A, how many? Look at this. From C to A, how many? You tell me. How many from C to A? So you can notice there are 2. What you can do, either you can go from C to C, then you can go to A, or you can go from C to A, then you can go to A. So there are 2, yes or no? Either you can do CCA, or you can do CAA. There are 2. So that is the reason you can notice here you are getting the value 2. Next, 101. So this will give you 1. 101. Okay, this will give you 1. So can you notice this M square is the same as that you are getting here. This M square is giving you ABC, ABC. Okay, and this M square is giving you 111, 101, 211. And that is the same data that you have here. Okay, the same data you are getting from this. Is this clear to everyone? Let me know. So this is the conclusion. So if you do power n, then what will happen? So with the induction, you can prove it. Okay, you can apply the induction. But if you do the power n, then what will happen? If you do power n or power k, basically, if you do power k, then what will happen? So power k will give you walks of length k. Okay. So this power k, you can notice this m power k gives number of walks of length k. Number of walks of length k between every two vertices. Is this clear? So this is important, that m power k will give you number of walks of length k between every two vertices. Between every two vertices, how many walks of length k are there? That will be given by m power k. You can just calculate m power k and it will give you number of walks of length k. Length exactly k. Okay. This is the conclusion. So this is the final conclusion, that if you see the adjacency matrix, entry I comma j in a power s, it will give you number of walks from I to j of length s. Okay. So a power k will give you number of walks of length k. A power s will give you number of walks of length s. A power n will give you number of walks of length n. A power 1000 will give you number of walks of length 1000 between every pair of vertices. Okay, clear or not? So for example, you can notice the entry in m power n will give you number of walks of length n. This is the point. Let's see this question. Consider this on your screen. This is a graph. This is a directed graph, correct? And this is the adjacency matrix. So this I have taken from this. There is a YouTube video. Okay. So from this YouTube video, I have taken this serial now. So the name of the YouTube channel is serial. So that is the reason. So credits to serial for this example. So you can see this is the example on your screen. This is a graph, directed graph, and this is the adjacency matrix. Okay. This M. What is this M? This M is basically the adjacency matrix of this graph. Okay. You can check it out. For example, you can notice from A to B, C, D, E, there is edges. From A to B, from A to C, from A to D, there are edges. Okay, from A to E also. So these are the edges. Now, this is the graph that is given to you. Adjacency matrix you have. Now you can easily see what this adjacency matrix is telling you. Tell me. Can I say this is m power 1? So what this is telling you? What this is telling you? This is telling you number of walks of length 1 between every two vertices. Between every two vertices, how many walks of length 1 you have? For example, between D, F, there is no walk of length 2. Length of 1. Yes or no? For example, you can notice, look at this example. Between D, F, there is no walk of length 1. There is no walk between D, F. You can check. There is no walk of length 1. Okay, but you can notice that between D, G, there is a walk of length 1 from D to G. Similarly, you can notice from F to B, there is walk of length 1 from F to B. And you can notice from F to E, there is no walk of length 1. So this is your table. So this table, basically this m power 1, it gives you number of walks of length 1. Number of walks of length 1 between every pair of vertices. Between every pair of vertices, it gives you number of walks of length 1. Is this clear? Shall I move on? Tell me, should I move on? Now let's see the m square. Now something interesting. Now this is your m, this is your m. Let's do the m square. If you do this cross this, then what you will get? Then you will get this matrix you will get. Okay, this matrix you are going to get. Now what this matrix is telling you? Tell me what this matrix should give you. This is your m square. What this should give you? Tell me. A simple question I am asking. What this should give you? This m square should give you walks of length 2. Yes or no? So you can notice this m square gives this m square. It basically gives number of walks. How many walks are there of length exactly 2? Between every pair of vertices. Okay. And you can check this is actually true. You can check it. For example, can you justify this value 2? Can you justify this value 2? Tell me, can you justify this value 2? Yes. Between A comma B, how many walks of number of walks of length 2? Just focus on number of walks of length 2. Focus on number of walks of length 2 from A to B. How many? From A to B. So from A to B, what you can do? From A to B, what you can do? Tell me. How many walks you can create of length 2? You want to create of length 2. So you can go from A to C and then you can go to B. Okay, either you can do this or you can go from A to E and then you can go to B. Either you can do this. So that's it. Only 2. Isn't it? Yes or no? Only 2. And that is the reason this value 2. So this value 2 we have seen. Now let's see this value 0. From B to F, do we have any walk of length 2? From B to F, do we have any walk of length 2? Any walk of length 2? There is no walk of length 2. Remember, there is walk of length 1. Yes or no? Are yes or no? There is walk of length 1 from B to F. From this vertex B to vertex F, there is walk of length 1. That is the reason you have 1 here. That is the reason you have 1 here. So from B to F, there is walk of length 1. But there is no walk of length 2. So that is the reason this 0 you have. So this 0 you have because no walk. None. Now finally, for example, what about this? From C to A, how many walks of length? From C to A, walks of length 2. How many walks of length 2 we have from C to A? So there is only 1. You can go from C to B and then you can go to A, CBA. This is the only thing. So that is the reason this value 1 is here. Okay, so like this. And you can notice this value. From A to A. From A to A, how many? Either you can do this, or you can do this, or you can go from E to E, E to A. So, okay, so you can easily see there are 4 from A to A. You can go from A to B and then you can go to A. You can go from A to D, then you can go to A. You can go from A to E, then you can go to A. Or you can go from A to C and then you can go to A. So there are 4. So this value is 4. So I hope this point is clear. Like what this is telling you, this A square, what this is telling you. Okay, similarly, this is A power 4. If you do A power 4, this you will get. Of course, don't do this. Don't do this multiplication. But I'm telling you that if you do A power 4, this value you will get. So what this is telling you, tell me. What this value tells you. What this value tells you. Just tell me, what is this 28? What is this 28? Is this number of walks of length 4 or at most length 4? Is this number of walks of length 4 or at most length 4? Of length 4 or at most length 4? Of at exactly length 4. Okay, number of walks of length 4 from A to A. Okay, so from A to A, there are 20 walks of length 4. There are 28. Okay, and so on. So this is the table for A power 4. So I hope you understood this. So this is your result. So that's it. We have seen very important result that, again, I'm just telling you, this is the final result. And this is extremely important because we will see the applications of it. What is the result? The result is that you have whatever graph you take. This graph can be directed. This graph can be directed or undirected. Whatever graph you take, directed or undirected, in any graph, what will happen? For this graph, there is an adjacency matrix. You have this adjacency matrix M. Okay. And this is the result that if you do M power K, if you do M power K, this K can be any number, any non-negative number, any non-negative integer. Okay. So if you do this M power K, where basically, sorry, this K is basically greater than equal to 1. So if you do this M power K, then what it will give you? This M power K tells us the number of walks, of length exactly K from between any two vertices, between any pair of vertices, between every pair of vertices. Okay. So this is what M power K tells you. So this M power K, this tells you number of walks. It gives you number of walks of length exactly K between every pair of vertices. This is your M power K. Like for example, just take this example. If you have this graph A, B, C, if you have this graph, then what your can you directly tell me what your M power 2 will be? Can you directly tell me for this graph? Can you directly tell me what your M power 2 will be? Like without calculating M power 2, can you tell me what your M power 2 will be? Without calculating M power 2, can you tell me what your M power 2 will be? So M power 2 will give you from A to A how many walks of length 2? So there is 0. It will be 0. And you can check it. It will be 0. You can check it. It definitely will be 0. Okay. If you check it, if you create M, okay, you create this M, if you create this M, this will be like 0, 1, 0. Okay, then you can notice from B to C, so this will be like this, and from C to A. So if you do this M square, then definitely you will get this 0, because there is no walk of length 2 from A to A. From A to A, there is no walk of length 2. From A to B, how many? Again, there is 0. It will be 0, you can check. From A to C, how many? There will be 1. From B to A, how many? There will be 1. From B to B, how many? There will be 0. From B to C, how many? There will be 0. From C to A, there will be 0. From C to B, there will be 1. From C to C, there will be 0. So if you multiply this, if you do M square, you will definitely get this. But you can directly create this. So tell me, which is easier? Which is easier, creating this M and then M square, or this? Okay, for simple graphs, if you have very simple graph, like small graph, if you have, then you can directly create this. Like for example, you can directly create M cube also. Can you create M cube? For this graph, can you create M cube? Let's see the M cube for this graph. What your M cube will be for this graph? So M cube will give you number of walks of length exactly 3. So you can notice from A to A, it will be 1 and everything else will be 0. From B to B, so it will be like this. This is what you will get. For this graph, M cube will be this. What your M power 5 will be? For this graph, like what your M power 7 will be? What your M power 7 will be for this graph? That will give you walks of length 7. Walks of length 7. So that is same as M power 1 actually. You can easily, for this graph, for this particular graph, you can easily see M power 7, walks of length 7, that is same as walks of length 1. So it will basically be your length of walks of length 1. So it will be same as M power 1. You can check. It will be same as M power 1. So for this graph, for this graph, I can say whether you do M power 7, that will be same as M power 1. They will be basically same. Okay, so like this. What about this question? If I give you another graph like A, B, C, this is the graph I give you, and let's assume this is the self loop. Now you tell me what your M square will be. Quickly tell me what your M square will be. Can you tell me what M square will be for this graph? So from A to A, how many walks of length 2? How many walks of length 2? Either you can do this. See, either you can do this, or you can do this, or you can do this self loop. So the answer will be 3. Correct? Walks of length 2. M square means walks of length 2. Okay, it will give you walks of length 2. Walks of length 2. So what you can do? It will be 3. How many walks of length 2? From A to A, you can notice from A to A, you can do this. Either you do this, or you do this, or you do this. So there will be 3. So this value will be 3. What about from A to B? From A to B, length, walk of length 2. That will be only 1. Okay, it will be, length of walk 2. That will be 2. Either you can do AAB or you can do ACB. Okay, so let me justify this. This will be either you can do AAB or you can do ACB. What about from A to C? From A to C, again it will be 2. What about B to A? From B to A. From B to A, length of 2. So there will be 2. What you can do? Either you can do BA then A, or you can do BCA. So there will be 2. Correct? Okay, let's see the next. So for example, B to B, there will be 2. B to B will be 2. Either you can do like this, or you can do like this. So B to B will be 2. From B to C, length 2, there will be only 1, right? Yes or no? There will be only 1 from B to C. From B to C, there will be only 1, and that will be of length 2. Of length 2. That will be like from B to A, then from B to C, from A to C. What about C to A? What about C to A? Tell me, what about C to A? Length 2. Okay, only look at length 2. So 1 will be this. Either you can have this, or you can go and you can just do this. So that will be 2. Okay, what about C to B? There will be only 1. What about C to C? There will be 2. So this is your table. Please tell me, did you get it now? We have taken enough examples. I hope you understood this. So this point is very important. What is the point? That whatever graph you take, directed or undirected, whatever graph you take, m power k will tell you number of walks of length exactly k. This is what m power k will tell you. If you do the power of adjacency matrix, that will give you number of walks of length exactly k between any two pair of vertices. Now we will see these applications of this concept. So let's see this in a next video. Okay. So the power, this is the concept we have seen, power of adjacency matrix. This is what we have seen. After 5 minutes, we will start a new video. In the next video, we will see the applications. These applications are very interesting. Okay. So immediately I am sharing the new link to you. Okay. In the next video, we will see. These applications are very important to remember, because in the GATE exam, the question will come from the applications. We will see 7 or 8 applications we will see. So far, whatever we have seen, those concepts you use. That is the reason these are called applications. Application means you apply the concepts that you have studied. All the concepts that we have seen in this lecture, these concepts you apply in all the 7 or 8 applications that we will see in the next lecture. Okay. So after 2 minutes, I will share the link of the next video. Okay. Thank you.